From the campus of Stanford University.
People are worried about data. They're worried about their privacy and their security. They should be. We need secure systems.
This is the future of everything.
But we can't have a system that closes that data off. It is too rich of a source of inspiration, innovation, and discovery for new things in medicine.
With your host, Russ Altman.
Today on The Future of Everything, the future of resilient and sustainable cities. So despite our evolutionary roots as hunter-gatherers, there's actually a large number of humans who are now living in what you might call the built environment, the result of our technology in creating buildings, bridges, infrastructure. And it includes not only where we live and work, but also where we spend time shopping, our athletics, our hobbies, our groups that we spend time with. It's bridges, it's electrical and water infrastructure, it's internet infrastructure, and all the components we assemble to create towns and cities. All of this infrastructure for life can be damaged and can have wear and tear in ways that we see in the news all the time. Earthquakes, rain, snowstorms, hurricanes, heat, especially when it alternates with cold, floods. Now, in 1989, just to tell a single personal story, in Northern California, we experienced the Loma Prieta earthquake, and it was a big one. It was, I think, above 7 on the Richter scale. I was a resident in medicine. Actually, I was a medical student at the Veterans Administration Hospital, and I was in the ICU, and I was about to present a new patient to the boss doctor, to the attending. And I literally was about to open my mouth to say something like, this is a 57-year-old man who just had a surgery or whatever. That presentation never happened. Because as I opened my mouth, there was a huge jolt to the left, and then it was followed by a jolt to the right. It became very clear that we were having a significant earthquake. Some of the patient beds had not been locked. The wheels were not locked. So in this ICU, 7 or 8 beds started rolling around. The ventilators, the breathing machines for 4 or 5 patients were disconnected. I don't think you need to be an expert to understand that having a ventilator be disconnected is a bad thing. So fortunately, we ran around, we reconnected the ventilators, we locked the beds, and then the rest of the month and months after that was the story of emptying out that ICU, emptying out, in fact, that entire building, which was subsequently condemned and taken down and replaced. It took months to do this. And this was a case of a total loss of a building. And there were many buildings in the area that suffered such losses. So we need to understand how our infrastructure can be damaged both over long periods of time with use and over short periods of time because of these sudden insults. And we need to understand how we can bounce back figuratively and literally, when we have this damage. Anne Kiremidjian is a professor of civil and environmental engineering at Stanford University. She develops sensing systems to monitor structures and their health, if you will, both before and after damage. She also combines this information with other sources to assess the readiness of a building or even an entire city to recover from disaster. And we have heard a lot that the U.S. Has not perhaps made appropriate investments in upgrading and maintaining infrastructure. And so the infrastructure may be fragile and too close to some sort of catastrophic failure. Well, is this true? And what can we do to protect people going forward?
To a great extent, that is true. And the reason why that is true is if you look at the stock of buildings and bridges and other infrastructure, and particularly water and power systems, sewer systems, they're very old. Most of the buildings that are vulnerable were built in the 50s and 60s and 70s. There were major
So 50 years old.
Yes. There were major changes in the building codes after the 1971 San Fernando earthquake. There was another major change after the 1989 Loma Prieta earthquake.
That was my ICU
right.
story.
That was another key event. The next major change that happened to the building codes was in 1994 after the Northridge earthquake.
Down in L.A.
Right, down in L.A. The reason those changes take place is that every time we have a significant earthquake, it shows us that we didn't quite understand how earthquakes affect buildings and other infrastructure, how they respond, what kind of damage will take place. For example, the 1994 earthquake showed us that what we believed to have been an invincible structures, namely, we thought that steel frame buildings are invincible to earthquakes. Literally, we said, we used to go around and say, steel frame buildings, nothing happens to them in any earthquake.
Basically, was the idea that they would bend but not break?
Correct. They can deform and return back to their original position. Well, Northridge earthquake showed us that that is not true. What happens is that because of the welding process, the connections of the beams and the columns, the welding process changes the properties of the steel. And that joint where we weld the beam to the column becomes a brittle joint. And during the earthquake, those members don't bend the way we expect them to bend. They crack at the joint. And in the Northridge earthquake, there were many, actually, I think majority of steel frame structures, multi-story steel frame structures that were subjected to significant shaking had cracks in the joints. And they all had to be repaired after the 1994 earthquake. Since then, the code has changed and design provisions have been made to avoid high stresses developing right at those joints.
So that means that going forward, when we built new buildings, they were in better shape, hopefully. But I'm sure we have a huge inventory of old buildings. And most people are not thinking we're going to just speculatively tear down our building and rebuild it safely. So people should know that, I guess, if they're in an older building, some of these weaknesses may still exist.
Right. In fact, right now, San Francisco is collecting data, and so is the city of Oakland. They're collecting data on the concrete non-ductile frames. They're called.
Can you help us parse through that? So concrete, we know what that is.
Yes.
What is a non-ductile frame?
So what we call a concrete non-ductile frame is a steel frame that typically was built in the 50s and 60s that has reinforcement in the columns and the beams. But the reinforcement, first of all, is very sparse. It's very widely spaced. Second, the tie bars are widely spaced, so you don't have enough confinement of either the beams or the columns. The second key feature of the concrete, non-ductile concrete frame is that the steel reinforcement does not go from the beam to the column at the joints in 90% of the cases. So you do not have an ability to transfer the loads from the beam to the column. And when the earthquake strikes, you have the beam and the column moving away from each other, cracking. You have major cracks developing.
And this is the brittleness, or at least
again,
related
brittle
to the
behavior is observed in these type of frames, and we have a very large stock of these type of buildings throughout the Bay Area.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Anne Kiremidjian about buildings and sustainability. Now, one of the things I know you've done, and it sounds very exciting, is you've created devices and methods for actually watching these buildings, if I'm not mistaken. So tell me a little bit about these sensors that you've helped create and deployed.
Right. Well, you mentioned the 1989 Loma Prieta earthquake, and the way I'm not an electrical engineer, so the way I got into this sensing and sensor networks and structural monitoring was after the 1989 Loma Prieta earthquake. I was sitting at a luncheon that was organized by then Dean Jim Gibbons of the School of Engineering, and the luncheon was primarily for the women faculty, and there were about 6 of us at the time.
Trailblazer.
Right. And it was a young lady sitting across from me, by the name of Teresa Meng. She was a professor in the electrical engineering department, and she started chastising me that it was 6 or 8 months after the Loma Prieta earthquake, and what's wrong with us civil engineers and structural engineers that we still don't know which buildings are damaged and which buildings are not damaged and what is the state. And then don't we have instruments that measure what the performance of the buildings are? And at the time, I was serving on the California Strong Motion Instrumentation Committee, which decides which buildings are supposed to be instrumented. And I explained to her that the reason why we don't have all the buildings instrumented is because it's a very expensive process. It's a very expensive thing to do. You know, the instruments, first of all, were this big. You know, they were huge.
Like the size of a bread box.
Yes, the size of a bread box, exactly. They were very expensive. They cost anywhere from $15,000 to $20,000 at that time.
Right.
Right. So that was a lot of money, and to put 5 to 10 instruments cost anywhere from $100,000 to $200,000.
Do you need more than one per building?
Oh, absolutely.
So you need to put them on different floors and the roof and all that kind of stuff.
The more instruments you can put, the better your predictions
so even
are
one
going
building could be hundreds of thousands of dollars.
Correct. That was a minimum at the time. And $100,000, you were able to install maybe 15 maximum.
What did they tell you? What are these
They
things
told you
measure?
acceleration at locations where the instrument is placed.
Okay, so if you have different parts of your building that are accelerating in different directions, that's not good.
You wouldn't. Well, you don't get a complete picture because the building is a system, so you hope to be able to model the system in some way. But having only 10 or 15 instruments is not sufficient to be able to analyze the structure and determine if there is.
So this conversation, it sounds to me, must have goaded you into a new.
Right. So to make the story short, she and I got together. She was working at the time on little robots that could crawl up and down. And I said, yes, but wireless sensors sensing is becoming much more. I should say, wireless communication is becoming available. We're talking 1990.
Yeah, before most of us had ever heard of Wi-Fi.
Right. It was. We're talking about cell phones and wireless communication. Also, at the same time, MEMS accelerometers were becoming
Could you
microelectromechanical
little
sensing.
tiny
accelerometers rather than a big box. You have now a little tiny. And at the time, those MEMS accelerometers were probably about half an inch by half an inch, which today they're 1/4 of an inch by 1/4 of an inch.
So way less than a bread box.
Way less than the big box. Right. So she and I got together, and we had a student who was very excited to work on this project, Eric Strasser. After several proposals, we finally got funding, and we developed the very first wireless accelerometer. This was a MEMS accelerometer that communicated wirelessly to your laptop. It sent all the information. And then we got together with Los Alamos National Labs and did a proof of concept. We installed 5 instruments, and they installed their instruments, their conventional accelerometers.
So you're comparing to the old technology.
Right. We did parallel testing, and we showed that indeed the MEMS accelerometers are just as good, if not even better, than what was used.
So are these now deployed around?
I wish I could say yes. The answer is not really. They are deployed sparsely, but for several reasons.
Huh.
Do you want to know why?
Yes, because I presume they were much cheaper than the $100,000.
So
that supply should not have been a problem. So the question is, why aren't every building in San Francisco instrumented?
Right. You would think that they should be instrumented, but so there are several barriers to adoption, and one is that the civil engineering profession is very conservative. And unless you have many proofs of instrumentation in real buildings over a period of time, they're not willing to adopt new technologies very easily. They tend to be very, very conservative. But some of the other things that we found out that really was very surprising to me, at least, we would talk to owners of large buildings in San Francisco,
Sure.
in Los Angeles, and the reaction was very frequently, well, if I put these instruments in my building, and if I find out that there is something wrong, I will have to spend the money to fix it. And the average owner of large building keeps the building for 5 years and then sells it. So they don't want to know if there is something wrong because
That is an amazing. So in
this
healthcare
was
we have
actually shocking to me.
It's amazing, and in healthcare we have a very similar phenomenon where because people only stay with an employer for 3 or 5 years,
Right.
the employer is not incentivized for the long-term health of the
Right.
patient.
Yes.
This is exactly the same
It
phenomenon.
is exactly the same thing. So owners don't want to know. So unless there are ordinances, and San Francisco at least passed one ordinance a while back, and they're looking now at developing some additional ordinances where buildings need to be instrumented. So the current ordinance says that any building that is 10,000 square feet or larger has to have at least one instrument. Yippity-doo.
What happens to the data? So if I have my one building and it has my one sensor,
Right.
Who's getting that data and who's monitoring it? Is it academics like you? Is there a government agency?
Well, typically the owner will have primary access to the data. And that's another issue,
Yes.
that they don't want anyone else to have the data.
Yes.
But the data doesn't do them any good. Yeah. Right now, there are buildings that are instrumented, and the state of California is instrumenting buildings all around the state.
They do have a long-term interest in these buildings.
Right. And California Geological Survey still has the same program that I was part of, known as the Strong Motion Instrumentation Program, and they are continuously instrumenting buildings. But coming back to the data, you can be streaming continuously, and things don't change very quickly in buildings. So you don't really need to stream continuously. So you have very large amounts of data that you're collecting that may not mean anything. It's just sitting there and you're gathering gigabytes and
Right,
terabytes
right.
of data. What do you do with
Somebody
it? So,
needs to be looking at it.
Right. So over the past 15 years, we've been focusing on developing algorithms that enable us to analyze the data. We had developed a scheme by which once you put your instrument in the building, if you have an extreme event, the instrument will wake up and collect the data. So if you have an earthquake, it will wake up and collect the data from the earthquake.
Yes,
But
yes.
if you don't have an earthquake, you don't need to collect data on a daily basis.
It can be stored locally?
Yes, it can be stored locally, but you also can schedule it to say, I'm going to collect data during off-peak hours, during peak hours, once a day or once a week,
Right.
once a month, during winter season, during summer season, during rainy season, and then check if something has happened. So our algorithms are intended to operate on board on the sensing unit itself. We have a microprocessor that once you have collected the data, excuse me,
Yes.
just a second.
No problem. We can start the sentence over again.
So once you have collected the data, we perform analysis on the data using modern machine learning statistical pattern recognition methods so that we compare the new data with previous data and we try to identify changes
Yes.
in the signal that enable us to predict that something has happened. So when we're talking about structural health monitoring, there are really three components to it that in the diagnostic part that we are interested. We want to know that, yes, something happened, where it happened, and what is it? Okay.
The underlying cause.
Yes. What is causing the change? Is it actual damage? Is it weather condition, changes in the weather condition? We need to know what it is. So right now, I have to say we have been successful in identifying changes. We are able to identify the general region. If you have a densely populated sensor system on a building, we can identify
Locate where it is.
Yes, where it is. We're still struggling with what are the most likely causes.
The root causes.
Right. So but some of the things. But for earthquakes, we have made some very interesting algorithmic development that. With our latest sensors, in addition to three-dimensional accelerometers, we have been deploying three-dimensional gyroscopes, and that has been enabled us to get estimates of the real-time displacements of the structure.
Yes.
And
Like
once
those jolts that I felt.
Right, these are the jolts, and those displacements can be related to the level of damage in the structure that is incredibly valuable, and we can issue alerts within literally seconds after the event has subsided.
We're going to get to that soon. This is The Future of Everything. I'm Russ Altman. More with guest Anne Kiremidjian about structural stability, monitoring, and preparing for the resilient and sustainable buildings of the future. Next on SiriusXM Insight 121. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Professor Anne Kiremidjian from Civil and Environmental Engineering about, well, what we have been talking about is buildings, monitoring their health, knowing when they're moving, and a little bit about the politics of what to do with that data and who's responsible for fixing them. But Anne, I know that one of your other interests that grows directly from this research is not just the individual building or the individual bridge, but the preparedness of a city or a region for these large-scale disasters. Tell me how you approach this from your disciplinary strengths in civil and environmental engineering, because these can be very complicated social economic issues, I would guess.
Yes, you actually touched on the right words there. So for a long time, actually from the very beginning when I started my research, I have been interested in regional hazard and loss estimation from earthquakes in particular. But most recently, the issue of resilience of urban regions has really
It's a very interesting idea.
Yes, yes. Well,
Not one that I would think of as a region being resilient. So
yes. So what are we talking about resilience? And indeed, it is a very interesting topic. What we recognized after some of the earthquake events that we've had and some of the hurricanes and storms like Superstorm Sandy and some of the hurricanes that have occurred, Katrina,
yes.
What we recognized that some regions recover very quickly and some don't, like New Orleans area after Katrina is still struggling. Puerto Rico is still struggling 2 years after the earthquake. Sorry.
And yet there are examples of cities that have done well.
Absolutely. New York City, after Superstorm Sandy, was functional within 3 months, probably about 80%, and 100% at most 6 months or so. Yes, there were little pockets here and there that still needed attention,
but not like New Orleans.
But overall, given the level of the severity of the storm, it did recover pretty quickly. So the notion of resilience has been brought up for some time now, and in fact, the Rockefeller Foundation established an organization called 100 Resilient Cities, and they are putting money to whereby they work with major metropolitan regions around the world.
So this is a global effort.
Yes, this is a global effort.
Because you also think about Japan and the tsunamis,
yes.
Indonesia. I mean, there's been a lot of stuff.
Yes, a lot of stuff that has gone on, particularly in the last 20 years or so. So the notion of resilience implies that a region that has been affected by an extreme event, by a catastrophic event, is able to rebuild its infrastructure, its building, its social, economic, and financial systems to the point where they're functioning at the same level as it was before the event, or even better level. Right. There are communities that have used the opportunity that when they're rebuilding,
Yes.
they're rebuilding to a higher standard.
There's that old saying, never let a good crisis go to waste. Because
Exactly.
it's sometimes an opportunity to fix a bunch of things that were broken,
Yes,
both figuratively and literally.
and literative, right? So exactly. So some communities, and hopefully, would be willing to rebuild to a higher standard. So our interests are primarily with our own background. How do we address resilience? So for a while, the definition of resilience floated around, but
It could be a lot of things.
Could be a
Everybody
lot of things.
has a different...
But in a nutshell, when we talk about resilience, what we're saying is we have to have the financial, the capital, we have to have the workforce, the supplies, the political will, the expertise to be able to rebuild. We have to include the social and economic components to be able to rebuild.
This is the future of everything. I'm Russ Altman. I'm speaking with Anne Kiremidjian about resilient cities. And what you just listed indicates to me that this resilience doesn't have to be a surprise. It's not like, oh, look, this city did well, this city didn't well. That these things might actually be predictable and manageable.
Yes.
Ahead of time, where we evaluate along all these axes that you just described and say, this city has a problem, this city looks like it's in pretty good shape.
That's correct. One other component that I didn't mention is time. We want that recovery to take place over a reasonable amount of time. And what is reasonable amount of time? It shouldn't be years. It should be months. It should be several months. So a city is considered, an urban region is considered to be resilient if it can rebuild within a reasonable amount of time.
Now, I find this interesting because you're a civil engineer, and so
Right.
you have the building part of it well within your core disciplinary expertise. But tell me about the other types of people that you need to engage to get kind of a 360-degree understanding of whether a region is looking like it's prepared.
Oh, my goodness. It requires that you interact with social scientists, with economists, with political scientists. You're asking why political scientists? Because you need to have certain policies that you may want to put in place before the event and have policies that would be available to you after the event. So we need engineers, not just civil engineers, but we need the electrical engineers. We need bioengineers because we are concerned about biohazards.
Yes.
We need just about all discipline. We need doctors. We need, you name it.
Are
It
the
has
civic-
to be a conglomeration of all different technical and non-technical fields.
Are the civic leaders open to this? When these very highly interdisciplinary groups get together and then go to the leadership of a county or a city or a state, is the leadership open to this, or is this just like you were describing before, a bunch of bad news and new expenses for them that they don't want to think about?
Well, fortunately, major cities have recognized their vulnerability. Many of them have seen what has happened, even if they didn't experience that themselves. They have seen what other cities have experienced. So what we're seeing now, San Francisco has a city resilience officer, and he has his staff that does look at the resilience of San Francisco. The same thing for Oakland, the same thing for Los Angeles, the same thing for New York. There are
So they have resilience offices.
officer who
That's
is in-
amazing.
Yes, and with a person in charge who has to develop a resilience plan for the city. They have to identify what are the needs. First of all, they have to identify what are the vulnerabilities of the city, and where are the greatest needs to be addressed before the event, and trying to have appropriate supplies, appropriate workforce, the number of engineers that need to be going around. So it's a very complex issue. Identifying where the problems are is also a major part of it. And actually, USGS together with...
This is the U.S. Geological Survey.
U.S. Geological Survey together with the Earthquake Engineering Research Institute just completed what is known as the Haywire study. In fact, tomorrow evening, they're having a presentation in Oakland showing what are the consequences of a major earthquake on the Hayward Fault? As we know, the Hayward Fault is greatly can erupt at any time.
So one question to finish up is for somebody who's thinking about this, who's just a private citizen, is there anything a private citizen could do to either help guarantee their own resilience or the resilience of their community? Or is this something you really just have to leave to the leadership?
Oh, absolutely not. Every person should take some responsibility. There are resources where individuals can go either on the U.S. Geological U.S. Geological Survey's website that lists various things that individuals can do to have supplies for at least 2 or 3 days or up to a week, because you may not be able to leave your house. You may not have. You may not be able to get access to gasoline to be able to drive your car.
Preparedness guidelines.
Yes, they're preparedness guidelines. They're also on the Structural Engineers Association of Northern California regionally. You can go on their website, and there are specific things that you can do to prepare yourself. Office of Emergency Services in California, again, has specific recommendations that individuals can do.
This is very reassuring because people trust that the leadership is acting, but they also need to do whatever they can to in their normal workplaces. Well, thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime, on demand, with the SiriusXM app.